So we want to look at a couple of examples for the photoelectric effect. One's a real simple example, one is a more common type of example. So we want to just determine the stopping voltage of an electron if the photoelectric surface has a work function of 1.30 EVs and the incoming photon has a wavelength of 665 nanometers. Alright, let's have a look at what's going on. So, we know from the photoelectric effect, we know that we're going to have to use conservation of energy. So we have the energy coming in from the photon. We have this HF, and then this is going to be equal to the work function plus the kinetic energy of the electron. Now, based on what I have wavelength of the photon, so HF is not really going to help me out here. So I'm going to change this to HC over lambda. This is our energy of the photon as a function of wavelength. The work function we're not too worried about. And then kinetic energy, I'm going to put that as Q times V stop, since we want stopping potential, and I can write kinetic energy as a function of stopping potential. So at this point, what I would like to do is I would like to determine the stopping voltage, so I need to rearrange for this. So first off, what I'm going to do is I'm just going to solve for QV stop. So I'm going to solve for QV stop, and then I'm going to do this as HC over lambda minus W. Now, you'll notice I have the work function in electron volts. This tells me I should probably use electron volts in here. I'm going to be really careful with that. I'm actually going to convert things to joules. When we're dealing with stopping potential, you have to be really careful with the units and really fussy with them. There's some trickery involved, but I'm going to convert that 1.30 electron volts. I'm going to convert that to joules, just because I don't want that. So we know that every electron volt represents 1.60 times 10 to the minus 19 joules. So we're going to say that this represents 2.08 times 10 to the minus 19 joules. So I can calculate this QV stop. So this is going to be my Planck's constant in joule seconds, my 3 times 10 to the 8 meters per second. We're going to divide that by our wavelength here, and then we're going to subtract off that work function in joules. So it has to be in joules to make sure that the units work. Because if I look at the units on here, I have joule seconds, meters per second, so that second will get rid of that second. This meter will get rid of this meter. So all I'm left with here is joules. I can only subtract or add the same units, so if I'm subtracting, I have to have the same units. That requires this to be in joules. So the next part is let's actually calculate that. So if we calculate this difference, we're going to get that QV stop. It's about 9.1098 times 10 to the minus 20 joules. So the last thing I'd like to do is I'd like to actually just calculate the stopping voltage. So I'm going to divide both sides by the elementary charge. So we're going to have this 9.1098 times 10 to the minus 20 joules divided by 1.60 times 10 to the minus 19 coulombs. So what I'm going to get for this is I'm going to get that the stopping potential is about 0.57 volts. So that's certainly a common question that we deal with when we're dealing with stopping potential. The other type has to deal with speed, and this one gets a lot of people. There's a few little tricks in here, but we'll look at the next one. So we want to find the maximum speeds of electrons that are emitted from a surface. It has a work function of 2.12 EV, and it's illuminated by indigo light of 450 nanometers. So let's have a look at this. So again, with the photoelectric effect, we want to use conservation of energy. So we're going to use conservation of energy. So we have the energy of the photon coming in. So I'm going to say that this is HC over lambda, because I want it as a function of wavelength since that's what I've been given. And then when we're talking about the electron, we have the work function, the energy required to liberate it, plus that maximum kinetic energy of the electrons. How we solve this, some people would say, okay, well, kinetic energy is half mv squared. I can rearrange that for v. You can do all that. That's fine. I would recommend solving for Ek first, then using half mv squared. Do it in 2 steps, just because it makes life a little bit easier. So Ek max is going to be this hc over lambda minus the work function. So the work function in eV, maybe this time, yeah, I'll use Planck's constant in electron volts seconds. So I got this 4.14 times 10 to the minus 15 electron volts seconds. We got that 3 times 10 to the 8 meters per second. We're going to divide that by that wavelength of 450 nanometers, and then we'll subtract off this 2.12 eV. Now, as I've said before, and I will always say it again, check the units just to make sure that they're doing exactly what we expect. We want to make sure that what we're doing is right and proper. So this second here is going to cancel that second in the bottom here. That meter up top is going to cancel that meter in the bottom. So I'm going to have electron volts minus another electron volts. The units are going to be fine. So I'm going to get that this is 0.64 eV. Now, you will have to convert this to joules because Ek equals half mv squared only works with SI units. So mass has to be in kilos, speed's going to be meters per second, which means E has to be in joules because we need, for the units that cancel out, we would need that joule to be converted into kilogram meters squared per second squared. So this has to go into joules. So Ek must be in joules to use Ek equals half mv squared. So there's no way around that one. So what that's going to tell us is that our kinetic energy, so Ek being 0.64 electron volts, if we multiply that by 1.60 times 10 to the minus 19 joules per electron volt, that's going to tell us the kinetic energy of this thing is about 1.024 times 10 to the minus 19 joules. Now that we know the kinetic energy, this is going to allow us to determine the maximum velocity. And I'm not writing the word max on these like I should be, it's implied. So we also know from Physics 20 and Science 10, Ek is equal to a half mv squared, or we know if we do the rearrangement, V is equal to 2 times Ek divided by the mass of the electron, since that's the thing that we're actually looking at the kinetic energy of. So the maximum speed of this thing, 2 times that 0.124 times 10 to the minus 19 joules divided by the mass of the electron. And again, I'm going to emphasize Ek with my pretty pink pen. Must be in joules with an exclamation point. So that's got to be in joules, otherwise you're going to get an answer that makes not a lot of sense. So if we do this and we're really careful with everything, we are going to get the answer is about 4.7 times 10 to the 5 meters per second. So the max speed of this electron being emitted is about 4.7 times 10 to the 5 meters per second. Couple of ways to spot errors. Big one, students forgetting to square root this. If you forget, you will get about 2.2 times 10 to the 11 meters per second. That's greater than the speed of light. That should be a red flag. The other really common mistake, forgetting to convert Ek into joules. If you forget to do that, you will also get a speed greater than the speed of light. So the moment you see a speed greater than the speed of light, the red flags and the alarm bell should be going off. Those are meant to kind of highlight, hey, you got to fix this. But this is also a fairly common type of photoelectric question that you could see on an exam.